Hello everyone, in this lecture we would like to discuss phonons 1 crystal vibrations. Now assuming that we have an elastic vibrations of crystal with one atom in the primitive cell, and we would like to find the frequency of an elastic wave in terms of the wave vector, which describes the wave in terms of the elastic constants. In the previous lecture we discussed crystal binding, and we also discussed that we have here two types of interactions, repulsive and attractive interaction, like this one here. And when they attract each other, they will overlap here, and this violates Pauli exclusion principle. So it is attractive here, and this one is repulsive interaction here. Now atoms in this case oscillates this way along the wave vector, or oscillates this way perpendicular to the wave vector, as in this figure. They are oscillating either in this way here, in this direction, and the wave vector in this direction here, and also oscillates in this direction, this one here, and the propagation in this one here. Now U in this case is called the displacement here, and the displacement number 1 is the same direction as the wave propagation, and the wave in this case here, it's longitudinal, and the displacement for the second case, this one right here, the displacement is perpendicular to the wave vector. In this case here, it's a transverse wave. So atoms, when they interact with each other, they vibrate along the wave vector or perpendicular to the wave vector. In this lecture, we will discuss how these atoms interact and what is the frequency of an elastic wave. Now let's assume that the force on the plane, let's name it S, in this case this one here, this plane here, caused by the displacement of the plane S plus P, and is proportional to the difference with US plus P minus US. For simplicity, let's consider only nearest neighbor interactions. So in this case here, Hooke's law here, it's equal to C, it's a force constant, times the displacement plane S plus 1 minus US plus C US minus 1 minus US. This one right here. The next plane, this one here, US plus 1 minus US, and the previous one, it's US minus 1 minus US. We're looking here for the displacement. This one is the displacement, and C is the force constant. Now, from Newton's second law, remember, sum of all forces equal to MA. In this case here, M partial to the displacement US dt square is actually equal to this F here. This is the only F we have in this situation, and we just simplify this one here. You will get C times US plus 1 plus US minus 1 minus 2 US, and this is called equation of motion. Now we will look for solutions with all displacements having the time dependence, which is E2 minus I omega t, time dependent solution. So in this case here, partial to U S partial t square equal to minus omega square US. Therefore, minus M omega square us equal to C us plus 1 plus us minus 1 minus 2 us. And this is a difference equation in the displacement u, which has traveling wave solution, which is in the form, the solution for this one here, us plus minus 1 equal to u exponential iska times exponential plus minus ika. In such a way, k here is the wave vector and a here is the spacing between planes. If we substitute this solution, this one right here, with the solution, this one here, we will get minus omega square mu exponential iska equal to C u exponential I s plus 1 ka plus exponential is minus 1 ka minus 2 exponential is ka. Now when u exponential iska cancel out, the remaining will be omega square m equal to minus c exponential ika. Remember, iska cancel out with this one here, and the remaining is exponential ika plus again e2 minus ika, because iska cancel out, minus 2, this one here, the iska cancel out. Now let's use the cosine identity here. Cosine theta, remember, it's equal to I theta minus e2 minus I theta over 2. If we use this one here in this one here, we will see that 2 cosine ka equal to exponential ika plus exponential minus ika. Therefore, the dispersion relation in this one here, omega square equal to 2c over m, this one here, times 1 minus cosine ka. And this is called dispersion relation. And from this one here, the boundaries of the first Brillouin zone is k equal to plus or minus pi over a. And the slope of omega versus k will be 0 at the zone boundaries, which means d omega square by dk equal to 2c a over m sine ka equal to 0. Now at the zone boundaries, at k equal to plus or minus pi over a, in this case here, sine ka will be equal to sine plus or minus pi. Now it doesn't matter, because sine pi or minus pi equal to 0, this one here equal to 0. Now by using the trigonometric identity, 1 minus cosine ka equal to 2 sine square half Ka. In this case here, omega square will be equal to 4c over m sine square half Ka. And in this case, omega equal to 4c over m to the power half sine half Ka. Now if we plot omega versus K, let's see here, this is omega over 4c over m half, and this is the zone boundaries, a 0 plus pi over a, and this one here 2 pi over a. Now at the zone boundaries, when K here it's equal to minus pi over a, the omega over 4c m, this one here, will be maximum, because if K here it's equal to minus pi over a, this whole thing it's equal to 1, and in this case omega divided by 4c over m to the power half, it's equal to 1. So this will be 1 here. Now at the zone boundaries, when K equal to 0, this will be 0, omega here will be 0, so it will be something like this. Again, when K equal to plus pi over a, omega will be maximum, which is 1 in this case, so it will be something like this. And again, at 2 pi over a, it will be 0. So omega in this one here over 4c over m to the power half is actually equal to sine half Ka. And this is one right here. And remember, this is the first Brillouin zone, and this one here is K. Now back to the equation, let's just rewrite it. S plus minus 1 equal to u exponential iska exponential plus or minus ik. Now the ratio of the displacement of two successive planes is given by us plus 1 divided by us equal to u exponential is plus 1 ka u exponential iska, which equal to exponential ika. Notice that the range minus pi to pi for the phase Ka covers all independent values of the exponential. So in this case here, Ka is actually greater than minus pi and less or equal to pi, or we can say that K in this one here, it's greater than minus pi over a and less or equal to pi over a. Now we actually focus on the first Brillouin zone, because if someone wants to treat the value of K outside the limit, now by subtracting the integral of multiple 2 pi over a, you will get back to the wave vector inside these limits. For instance, assuming that here K is outside the first zone, then in this case here, K prime, the new wave vector, will be equal to K minus 2 pi n over a, which again lies within the first Brillouin zone. And for that reason, the ratio between successive planes will be equal to e to I ka. That's what we just find in this one here. Now, if we substitute the new k prime with vector, we will get in this one here e to I 2 pi n times exponential, this is exponential, I ka minus 2 pi n, which equivalent to e to I k prime a. And again, we just get back to the same solution, because e to I 2 pi n is actually equal to 1, and again we get back to the same as inside the first zone. An important note we have to consider here is at the boundaries, when k maximum here equal to plus minus pi over a, for this case here, the solution us in this case will equal to u e to I s k a, and which does not represent a traveling wave, but it's actually a standing wave. So at this one here is standing wave. And at the zone boundaries, s k max a is actually equal to plus or minus s pi. For that reason, us here equal to u exponential plus minus is pi, which equal to u minus 1 to the power s. And again, this is standing wave. As we can see here, an alternate atoms oscillate in opposite phases, because us here it's equal to, it's either plus or minus 1 depending on the s value. If s is even, then u in this case equal to plus 1. If s is odd, us in this case it's equal to minus 1. In either case, it is a standing wave. Now let's define the group velocity. The transmission velocity of the wave packet is called group velocity, and it's given by Vg equal to d omega by dk, or the group velocity it's equal to gradient k omega of k. Now back to this dispersion relation, omega equal to 4c over m to the power half sine half ka. And from this one here, the group velocity is equal to c a square over m to the power half cosine half ka, which is, as expected, is 0 at the edge of the zone boundaries when k equal to pi over a. The group velocity it's equal to 0. Now let's consider the long wave length limit. When ka is much less than 1, we expand cosine ka equal to 1 minus half ka and ignore the higher orders, in this one here, omega square equal to C over M K square A square, and remember when Ka here is much less than 1 for the long wavelength limit. And this leads to group velocity equal to omega over K. Back to the previous equation, let's just write it down. Omega square equal to 2C over M 1 minus cosine Ka. Now, as a generalization for this one here, for all P nearest planes, we will find that omega square equal to 2 over M and summation P is greater than 0, Cp 1 minus cosine Pka. Cp here is called the interplanar force constant. And to find Cp here, let's multiply both sides of this equation with cosine Rka and integrate both sides from minus pi over a to pi over a. These are boundaries. And in this case here, m times integration minus pi over a to pi over a dk omega square k cosine Rka is equal to 2 summation p is greater than 0 Cp minus pi over a to pi over a dk 1 minus cosine pka cosine Rka. Now this integral vanishes except the case when p equal to r. Now when p equal to r, in this case here, Cp equal to minus ma over 2 pi integration minus pi over a to pi over a dk omega square k cosine pka. And this one right here gives the force constant at the range Pa for a structure with monoatomic bases. So this one here is force constant for monoatomic bases. Now, let's consider another case when we have two atoms pair primitive bases. When we have one atom pair primitive bases, we're actually having only acoustical modes. When we have two atoms pair primitive bases, two modes will develop for each polarization. And these two modes, acoustical and optical. Now, in acoustical modes, we have longitudinal acoustical and transverse acoustical. So this one here is longitudinal acoustical, and this one here is transverse acoustical. Now, if we have p atoms in the primitive cell, therefore we will get 3 p branches develop. Now, 3 of these 3p branches are acoustical branches, and the rest, which is 3p minus 3, are optical branches. Now, as a generalization, if we have p atoms in the primitive cell and n primitive cells, therefore we will have pn atoms, and each atom will have 3 degrees of freedom. In this case, we will have 3p n degrees of freedom for the crystal. Now, the number of allowed K values in a single branch is just n for one Brillouin zone. Actually, we will have one longitudinal acoustical branch and 2 transverse acoustical branch. For that reason, the longitudinal acoustical branch and 2 transverse acoustical branches will have a total of 3n modes. And the rest, which is 3p minus 3 times n, here degrees of freedom, are accommodated by the optical branches. So this one here is optical branches, and 3n acoustical branches. And remember, 1 is longitudinal and 2 is transverse. Now, let's assume that we have a cubic crystal with 2 atoms, M1 and M2. As in this one here, as we can see, we have here 2 atoms, this one here, right here, and the displacement for the first atom is US, and the displacement for the other atom, it's VS. In this case here, let's write down the equations of motion. M1 for the first atom, d2us by dt square is equal to c is the force constant. And remember, we're taking the successive planes. If this is us here, this one here, now vs, this one here, minus us plus us minus 1 minus us. So in total, it's equal to vs plus vs minus 1 minus 2 us. The equation of motion for the second atom, s by dt square, it's equal to c, and this is vs here, this one here. Now the successive plane, this one and this one here, us plus 1 minus vs and us minus vs. For this case here, c us plus 1 plus us minus 2 vs. We're actually looking for a solution in the form of traveling wave. Now, the solutions for this second order differential equations, we're actually having 2 solutions, us equal to u exponential iska times exponential minus I omega t, and v2 equal to v exponential iska times exponential minus I omega t. Now, when we substitute these solutions in these 2 equations, this one here and this one right here, we will get minus omega square m1 u equal to cv 1 plus exponential ika minus 2cu, and we substitute the second equation, this one here, you will get minus omega square m2v equal to cu exponential ika plus 1 minus 2c v. To solve these two equations, let's just put them in a determinant here. 2c minus m1 omega square minus c 1 plus exponential ika minus c 1 plus exponential ika 2c minus m2 omega square, and this whole determinant equal to 0. Remember, this with this minus this with this, you will find that m1 m2 omega to the power 4 minus 2c m1 plus m2 omega square plus 2c square 1 minus cosine ka, this whole thing equal to 0. To solve this exactly for omega square, now let's use the general rule, minus b plus or minus square root of b square minus 4ac divided by 2a. Now let's just use it in this equation here. We will get omega square equal to 2c m1 plus m2, this is actually b, plus or minus square root of 4c square m1 plus m2, whole thing square, minus 4 m1 m2 2c square 1 minus cosine ka, and this whole thing divided by 2m1 m2. Now omega square equal to 2c over 2m1 m2 m1 plus m2 plus or minus m1 plus m2 square minus 4m1 m2 sine square ka over 2, this whole thing to the power half. Or C m1 plus m2 m1 m2 plus or minus m1 plus m2 m1 m2 square minus 4 m1 m2 m1 m2 square sine square ka over 2 to the power half, and let's simplify it more. 1 over m1 1 over m2 plus or minus 1 over m1 plus 1 over m2 square minus 4 m1 m2 sine square ka over 2 to the power half. Now let's take different cases for k. Case 1, when k equal to 0, for this one here, omega square is equal to c 1 over m1 plus 1 over m2 plus or minus 1 over m2 plus 1 over m1. And we actually having here two roots, the positive root and the negative root. So the positive root for the plus here, omega square equal to 2c 1 over m1 plus 1 over m2. Now the negative root, omega square is equal to 0. Now let's consider the other case, case 2, when k is actually equal to plus or minus pi over a. Now you substitute k back in here, this one right here, this one here, you will get omega square equal c 1 over m1 plus 1 over m2 plus or minus 1 over m1 square plus 1 over m2 square plus 2 over m1 minus 4 over m1 m2 to the power half, and omega square upon simplifying this one here equal to c 1 over m1 plus 1 over m2 plus or minus 1 over m1 minus 1 over m2 square to the power half. Omega square equal to c 1 over m1 plus 1 over m2 plus or minus 1 over m1 minus 1 over m2. Now we have positive root, omega for this root is equal to 2c over m1, and negative root, omega is equal to, for this one here, omega actually square is equal to 2c over m2. Now back to the original equation, this one right here. Now let's examine this equation for the limiting cases when Ka is much less than 1 and when Ka is equal to plus or minus pi at the zone boundaries. Now for small Ka, we have here cosine Ka is approximately equal to 1 minus half k square a square plus etc. Now for that reason, omega square approximately equal to 2c 1 over m1 plus 1 over m2, and this is actually a optical branch and omega square approximately equal to half c over m1 plus m2 k square a square, and is actually acoustical branch. Now at k maximum equal to plus or minus pi over a, for that reason omega square will be equal to 2c over m1, and omega square, the other one, equal to 2c over m2. Now let's discuss quantization of phonons. Remember, the quantum of energy is called phonons. So phonons is the quantum of energy. Now each mode of the wave vector k is a simple harmonic motion of the whole crystal. With frequency omega k, we have quantized energy levels epsilon and equal to n plus half h bar omega, or an h bar omega plus half h bar omega, in such a way n is the excitation quanta and the other terms is 0 point energy. Now n is excitation quanta and the other terms is the 0 point energy. That's it. Thank you for watching.